Hi, my name is Tristan Linscott and this is my lab report for Lab 1 of Physics 1 at Georgia Tech. This lab uses a rolling ball to examine constant velocity. First, I will introduce the purpose and the experiment, followed by important principles and formulas that will be used. Then I will explain the procedure and experiment, show results, and finish with the comparison of our two models and important questions regarding the lab. Purpose. The purpose of this lab is to observe and analyze the motion of an object moving at a constant speed and direction, therefore constant velocity, and then develop a computational model based on physics principles to predict the object's motion. Then I'm going to compare the observed data with the model's predictions to assess the accuracy of the model and understand the assumptions that were made. Some important models and fundamental physics principles that were used. First, constant velocity. In order for an object to be moving at constant velocity, the sum of forces acting on the object must be zero. Newton's first law then states that every object that is at rest or in motion will remain at rest or in motion until another force is acted upon it. These formulas below predict the velocity and position of the ball and are derived from Newton's second law and will be used in our code and computational model. The first one is velocity, the second one is position, and below that is the momentum principle in Newton's second law that these come from. I have included helpful diagrams relevant to this lab. For this lab, we will assume that there is no friction and no air resistance affecting the ball. This would mean that there is no net forces acting on the ball. I had to apply a force to get the ball moving, as seen on the left, but once it was moving and at speed, it would maintain that speed and velocity. This is because the gravitational and normal forces left on the ball cancel each other out, as seen on the right. Here are some conditions to preface our experiment. I estimated that the dresser was about 1.5 meters long. And here is the procedure. Basically, we're going to observe an object moving at constant velocity and compare that to a model of the object's expected position versus time. Here's a screenshot of me using Tracker to analyze the video of the ball. In my video, the ball moves from left to right. Therefore, I made the axes such that left is positive and right is negative so I could obtain an upward sloping position versus time graph. For the computational model, I used the GlowScript code provided and edited where I felt was necessary. First, I left the mass at the default value of 1 because it did not affect the velocity calculations due to it canceling out. I then changed the ball's initial position and velocity to match that of my video recording and when my tracker began. Next, I inputted the starting time of my video as t and used the difference between each timestamp for delta t. I then used the earlier mentioned equations derived from Newton's second law to calculate velocity and position in my code. As you can see in the top right corner, we maintained constant velocity. A preview of our results would be that we would want them to stay fairly similar, but I'm going to assume that there will be some sort of difference due to friction we did not account for. This is correct. Here are the two graphs of both my experiment and the computational model being compared. We can see that they're quite similar at first, but as the time goes on, the graphs start to differ. The tracker's line starts to flatten, indicating a decrease in speed and velocity. This is due to friction against the ball that we likely did not account for. Now, some interesting questions to think about. 1. What would change if we flipped the axes? Well, for my experiment, I made left positive and right negative in order to get an upward sloping graph. If I were to flip the axes, it would result in a downward sloping graph instead. However, this would not affect my conclusions and observations and the differences at the end. Next, is it possible to see how many pushes and pulls are added together to give zero net force in this case? My answer is no. It's difficult to know how many forces are acting. We do know that net force isn't necessarily zero because we know that friction's occurring. However, there's just not enough information to determine all of the forces acting on this ball. To reduce this uncertainty, maybe we could factor in outside forces into our computations, or just use an object with little to no friction or resistance so we wouldn't have to worry about it. That is my Lab 1 experiment. Thank you.